Hi everybody, Mrs. Mancuso here with some more AP Bio review. So some people asked me to do some Hardy-Weinberg problems. So Hardy-Weinberg problems is when we're looking at population and how P and Q are changing. So if it's in equilibrium, P and Q are not changing. So when we do these problems, we're showing that evolution has not occurred. It's not really the normal thing. Usually evolution is occurring, and it's occurring because of five things. So you think of the five fingers on your hand. If you have a small population, that's genetic drift. Evolution will occur if you have a small population because by chance, the numbers aren't going to work out the same. So your P's and Q's will be different. Good examples of that are a bottleneck or a founder's effect. Bottleneck is when the size of your population drastically decreases, and founder's effect is when one part of your population leaves and starts a new population. The next one you can be reminded with the ring. So that is non-random mating. So when we sexually select our mates based on their traits, we are choosing what's favorable and what's not favorable. So that alters P and Q frequencies. The next one is mutations. Mutations is how you get new alleles. So new alleles will change the frequency of P's and Q's and essentially even add in another letter. All right, this is gene flow, genes entering and leaving a population. So when you have immigration and emigration, you're going to change your numbers because you're adding or removing members from your population. And then thumbs up for natural selection. So thumbs up is, this is an adaptation to have opposable thumbs. So when you have something that selects for in the environment, meaning that it is more fit and gives you an increased chance of survival, those alleles will increase in frequency and the opposite allele will decrease in frequency. So P refers to the frequency of the dominant allele, and Q refers to the frequency of the recessive allele, and together those should add up to 100%, which is 1.0 if you move it over two decimal places. So P plus Q equals 1. All right, in a population, your genotype could be big A, homozygous dominant, or big A, or little a. And this is P squared, this is 2PQ, and this is Q squared. And these should also add up to 100% or 1.0. So knowing that, we can solve any problem. So we can say, all right, if you have this autosomal recessive trait, that is present in 4% of the population, and my population has 25,000 people in it, and I want to know the frequency of the dominant allele and the frequency of the recessive allele, and I want to know how many carriers there are. So the first thing I do is I want to use this number. They've told me autosomal recessive, so that's little a. So that's Q squared. So I want to first change this out of a percentage, so 0.04. And then I find the square root of it. The square root of 0.04 would be 0.2. So this is equal to the frequency of the recessive allele. P must be 0.8 because these two have to add up to 1. And so the frequency of the dominant allele is a 0.8. Now if I want to find out the number of carriers, I want to figure out big A, little a. So that's 2PQ. So 2 times 0.8 times 0.2 gives me 0.32. And then I multiply that by my population size. So 25,000 times 0.32, I get 8,000. So out of a population of 25,000, 8,000 would have that carrier phenotype. So 8,000 people would be big A, little a. All right, another problem that I want to go over with you is sometimes they give you a data table and they'll tell you that nobody is little a. So that means that gets rid of the idea of doing the Q squared because I don't have any Q squared. So if I don't have the Q squared, I'm actually gonna have to count up alleles. So they'll tell me the frequency of these. So let's say I have 184 people that are carriers. And let's say big A, I have 636, okay? So this is what they gave me for the population, and I can't do my typical Q squared. So instead, what I have to do is actually count these alleles. So in a population, if I have 636 people that are big A, that means there's 636 plus 636 for those big A's, plus these 184 also have one big A. So the number of big A's, 636 plus 636 plus 184, is equal to 1456. And the total amount of alleles in a population is the amount of people times 2. So 636 plus 184 times 2 is equal to 1640. So there's 1640 alleles total. Alleles total. Of those, 1456 are big A's. So I can divide 1456 divided by 1640, and I get 0.89. So that tells me P. P is equal to 0.89. And then if I want to do my little a's, I have 184 little a's. I don't have any little a's, so the only little a's I have are 184 people have one each. So 184 out of 1640 is equal to 0.11. Which is awesome, because if my Q is 0.11, I would expect my P to be 0.89. So I know my math worked out. All right, so those are some examples of how you do Hardy-Weinberg problems. Thanks for watching.